So we are here to introduce a device from our neuromusic lab that wants to read brain activity and trigger and manipulate music in real time. So this is a product of a teamwork by myself, Kasia, and Hamid. So this is our agenda for today. I will start by outlining the urgent need for more effective motor rehabilitation methods. I will cover the pitfalls of conventional methods, and I will present the scientific basis for our solution. Then Hamid will discuss the BCI data processing, the actual data that we use. BCI stands for brain-computer interface, which is very key for the present project. It will also present benchmark models, and then Kasia will cover the winning model, the one that we actually used. I'm the neuroscientist, Kasia is the mathematician, and Hamid is the physicist, just to give you some background about us. All right, so let's start with some numbers. So global stroke incidence, we're talking about 12 millions. With nearly 90% of people experiencing hemiparesis, talking about the survivors. This other graph is for showing the amount of yearly of new amputees, especially for limbs. So it's clearly less than the global incidence of stroke, but then the cost and complexity of prosthetic care means that the financial burden of motor rehab is astronomical. So we're talking about, yeah. So why is the cost so high for motor rehabilitation? Because conventional rehabilitation is inefficient. And so for stroke survivors, it misses the golden window, which is a very critical early phase during which recovery can actually happen in the brain. And because these patients, to do conventional therapy, they need to actually wait until they're physically strong enough to move. And for amputees, conventional methods don't address the lack of intuitive prosthetic use. They don't provide sensory feedback, and they don't help with the associated issues, like, for example, phantom limb pain. So all this means that we have diminished outcome and long-term costs. So the way we overcome these limitations is by harnessing neuroplasticity. Neuroplasticity is the brain's ability to rewire itself. And our device directly leverages this process during the crucial early golden window that I was talking about before. So it's this early critical phase. We integrate two synergistic tools. One is motor imagery or mental practice. So this allows the patient to imagine the movement, which activates the same motor maps as physical movement. So as you see in this image, like the blue areas are those that overlap between actual motor execution and motor imagination. They're the same areas. So this mental rehearsal, so this mental imagination of actually moving drives motor map remapping in the brain. And then we wanted to combine rhythmic entrainment by using real-time music and drums. Particularly the association between movements and music and rhythm creates a very powerful synergy that allows to strengthen the connections between our auditory cortex and our motor cortex, and supports improved movement, improved gait, and improved coordination. So the result is enhanced clinical efficacy because we are directly targeting the brain, accelerated and intuitive recovery because, again, it's brain-led, and ultimately it's also it would allow to reduce costs because this can be done immediately, so people don't need to wait until they move to start with this therapy, and it's automated, so they don't need a one-to-one session. So this brings us to our solution, a brain-computer interface, a BCI device that takes the patient imagined movements and then it converts it into a tangible and musical output. So enough with theory. I'm going to play the demo. So we have an automatic music composer. So the first part is just the composer. So for the demo, I just picked a track and then I divided it into stems. And each movement will be associated with a stem. And so we start composing, and after all stems are layered, then you have the DJ part. So each movement is actually connected not with a stem, but with a different effect. I will only show you the composition part, and if you're interested, like reach out and you can check by yourself later.
After the exciting part, it's time for the lousy part. So I try to keep it as exciting as possible, but I will walk you through some of the important part of the machine learning. So namely data acquisitions, data formattings, data processing, and pre-processings. And also explain a bit about the model journeys, the model selections, and then so how we walked through, how we went through the selection of the different models and which model gives us the best and best accuracy and more highest precisions. So in principle, we started exploring different data sets. So, for example, physio nets and some other like toy model data from Kaggle's and other competition related publicly available data sets. We ended up using this data, which is firstly published in a Nature paper. So it's one of the largest, if not the largest one of the largest publicly available EEG and motor imagery data sets. And so here are some of the details of the data. So it contains of 29 sessions, like the recordings, number of recordings. So each recording session is roughly around 1 hour, 55 minutes or so. So it's composed of 22 channels. So basically in the language of machine learning, so these are the number of feature space, the number of dimensions of the features that we have. So, and the sampling rate for the EEG recording is 200 hertz for the paradigm that we use, which is called HALT. So it's in principle, we have 6 classes. So right and left hands, right and left legs, tongue, and so the neutral state. So of course, so in principle for the demo that you showed, and you can have access through the QR links that we have at the very end. So only the 4 states or 4 classes are used for the music compositions. So like after we took the data, so it is one important aspect of the EEG signals is that they are notoriously noisy. So they are very famous for being difficult to handle and very noisy. So just to give you a gist of how noisy these data sets can be, so I'm showing so on the left side the different channels. So these time series data are the output of something. A component is called ICA, independent component analysis, which basically it breaks or chunks the data, the raw data, into different into different components. So for example, here you can see that the eye blinkings, which is on the very top, is associated with the tomographic color maps that you can see on the left side. And so these are on the frontal cortex of the brain. So, and then you can see that how quickly these like unwanted acts like eye blinkings or muscle contractions, even the heartbeat can contaminate our data or EEG data. So then we need different types of pre-processing. So we basically went through several of the procedures and the aspects of pre-processing. So you can see some of them here. For example, fast Fourier transform, wavelet transformations, or even Gaussian filters and denoising. So, and also, as I said, it's also important epoching. So epoching in principle is the stage that we convert the continuous data sets, EEG data, into like a discretized or continuous data. So in principle, it's just like an analog to digital conversion, so to speak. So once we went through this laborious and lousy process, so we have we can use machine learning algorithms. So we went through different methodologies and machineries. So here is like a history of the journeys that we went through. So in principle, from the beginning, so our goal or target was just using the convolutional neural networks, deep neural networks. So instead of using conventional logistic regressions like random forest or even ensemble rendering like XGBoost or even SVMs. So we went through different approaches. For example, so here's the list, like a short list of them, like a conventional neural network, LSTM, long short memories. And also a method is called GERU. There is a family of them. We implemented several of them in PyTorch. But unfortunately, at in this stage, so the accuracy on the test data that we get were like stacking around 60-70%. So which is not bad, technically speaking, because we had 6 classes and like 60-65 was not bad, even good enough, but we were aiming for higher accuracy. So we also looked into, we used also the ResNet architecture. So we took the weight and biases from ResNet and then fine-tuned it for our own demand. So for the data set that we had. So the problem here we faced with was that it was quite good on the training data, but it was overfitting on the test data set. So also we used the weight and biases from VanDB for monitoring or visualization and hyperparameter trackings. So our journey of the model selections landed us on a model is called shallow net, which Kasia is gonna explain to you about.
So thank you very much. Let's go to the next slide. Okay, so that was a moment because we were stuck at the 60-70%, and that was a moment when, some break came. And so what we found this article where people, as you see, data scientists, computer scientists, and also, neuroscientists, they invented a series of models which could be applied especially for EEG's data. And we decided to try all of them, one by one. These models are implemented in the library called BrainDecode. Okay, so we started with Deep4Net, and that one was too heavy. So basically the previous models, they were too heavy. They had too many parameters. They were overfitting on the trained data, and predictions were not so good for validation. This model was not better than GERU, so we decided not to put him here, but with EEG-net, we already got above, so you can see the GRU, this violet, and then with the pink one, yeah, that was EEG-net, we came already over 60%, it was good. And then we tried the last one, and that was our breakthrough. Shallow let us get right away over 70%, and we were already happy with the model, but it was not yet. We wanted more. Yeah, we wanted, of course, more. Okay. Good. So let me show you a little bit the structure of the shallow. So this is from the original article. They also use it for prediction of motor imaginary movements. Basically, it has two convolutional layers, but as you see between them with some functions like pulling and dropouts and so on. But what is important here, between, there are some mathematical functions. Yeah, we were wondering why. So we adapted this model to our data, to our structures. As you see, we even have here some exponent function and so on. This is quite light model. It has only 38,000 parameters around. Yeah, so quite light for that purpose. And we were very happy with that already. Yeah. But then we try to think, if the model already works so well, maybe we should think about preprocessing. Maybe let's look again at the preprocessing. And we decided to change a little bit, remove certain preprocessing, and we got better. So we start to remove step-by-step preprocessing, and we got even better. Because in this original paper, it's well described that this function, they basically, what they do, they simulate preprocessing in a way. So they are hidden there. And so yes, we start to remove preprocessing, and you can see that without preprocessing, so the only one which was left was epoching that was necessary to leave, but all others was gone. Yeah, and without preprocessing, we went so high, yeah, over 0.8. I should mention now that this training was done only because, as you see, the EEG data, they are very much dependent on the person. Yes, they really depend. There is some common features that all of us share, but how much we didn't know. Yeah, so we trained the model first. We had one person who had 3 sessions, so like 3 hours of recording. On every session, this person repeated imaginary movement, one imaginary movement around 150 times, if I remember well. So quite a lot of data already from one person. And for that one person, we got already 0.8. We trained it only on 2 sessions. We left one for testing. Okay, so we didn't have preprocessing. And then we go now to our final model, optimal model. So then we thought, okay, so let's leave 2 sessions away. Yeah, let's take this person that we already left 1 session away. And then that was 1 session with 1 person only. So 1 person had only 1 session. We left these 2 sessions separate, and then we train. Now we used GPUs. We used Kaggle GPUs to train the model shallow on all sessions that we have, only not on the 2 ones. And already here we were quite happy. Validation accuracy was 0.71. Yeah. For multi-session was quite good. Okay, so we just pick up the weights. Yes, we took the target subject, so the session of the subject that we left behind, and we fine-tune for that. And you see how our model was doing very nice on validation accuracy already from the start. So very little fine-tuning, already was doing very well. Okay, and then let's see how that looks in the test. So in the test, we obtain something like that. So here you see this confusion matrix for the person that the model already knew, but not that session, knew from other sessions. So accuracy, as you see, so for, let's say, for true label and predicted label, you see how well model was doing. And I believe that the rest, it has to be like that, because you cannot do the one exercise 150 times without being tired and so on. And that's normal. And that's how the model was doing on the person that he never saw before, person and session. Yeah, so this is also not bad, I would say. Yes, and based on that model, we could build our little app, which is still under development, but the demo is there. Yeah? Okay, so that's it. We would like to thank Antonio, yeah, all our instructors. We learn a lot here. It was great. And our colleagues, thank you very much.